Thanks, Helen. I guess you can hear me? Good. Right. So yeah, this is a bit of a tag team, and so I know I'm going to get in trouble if I go over time. So I'll try and go fast. But it's really there's been quite a few people involved in some of this work, and really I guess the rationale here. Oops, went too far. Basically, the aim of this project is to take a lot of the results of the projects that you've just heard about for the last few talks and to pull them together into what you might do in a company to actually come up with targets for this style of mineralization or areas of interest or an outcome that allows you to actually then say, okay, well, this is an area I might go explore in. And so some of the things I talk about next 10 minutes or so are probably going to be a little bit of a repeat of what you've just heard. And you'll be happy to know I'm not really expecting you to read this very busy table, but what it basically summarizes is the approach that we've been taking, which is, we thought that there wasn't much use in going off and reinventing an approach that's been used over the last 10 years by GA, and they've produced a whole series of products in that area and really was pioneered by Leslie Wyborn and built on by other people, where you take an approach of saying, okay, well, where's the source of fluids and metals? What's the sort of transport or architecture of the system? Obviously, this sort of approach was also well developed during the PMD-CRC. What's we used to call it a trap, but I guess people are now preferring to call it a gradient because you're not actually trapping the fluids, they keep going if it's a hydrothermal deposit. And the energy source, the driver for this style of for different styles of mineralization. You can see what I've got up here is the range of different styles of mineralization that have already been touched on here, everything from phosphorites to unconformity rare earths to two different styles of deposit that I've separated on the basis of the fact that some of the previous work has done that. But I agree with what Ross and others have said more recently, and that is that there's an interesting distinction between stuff that's called IOCGs and stuff that's called other things, and it's not as simple as I think a lot of people have made out. Carbonatites, which are of course by far and away the most important source of rare earths on the planet. So I've considered that, as well as some of the other things like mineral sands, which are a potential source and historical very strong source for rare earths, Peralkaline Volcanics, and ion absorption clays, which we won't talk about too much in the context of this. So let's talk first about phosphorites, and this is one where really I think Matt just touched on some of the aspects that are important. I mean, the fluids are easy in this case; they're seawater. But where's the rare earths coming from? I certainly agree when you look at the pattern of endowment, and I'll come to it. That's come out as a very busy diagram at this scale. That the rare earth enriched mineralization appears to be related to areas where the basement of the Isa inlier is the erosional source for material that would have gone into deep water, whereas the areas further to the north where the Carpentaria Basin was likely to have been the erosional source are much less endowed in rare earths, and I think that's an important control. Actually, if I shoot ahead to the next slide, there's a simpler version of this. This is basically actually some work that Karen was involved in doing, mapping the position, the base of the Beetle Creek Formation. And what you can see here is that it's not just a nice simple basin geometry, it's actually quite strongly controlled by the basement architecture of faults, and that the actual zones of phosphorite are related to restricted lagoonal subbasins that are formed partly as a function of the geometry of these faults. And that's a critical control for the formation of phosphorites, combined with the composition of the underlying basement. So I'm going to move to carbonatites next. And of course, why are you talking about carbonatites? There aren't any in Queensland. The reason I'm talking about carbonatites is that when you actually look at carbonatites, they are really just about the most unsubtle magnetic target that you could think of. So I've just included some examples there. Mount Weld, which is obviously one of Australia's best carbonatites, a whole series from, unfortunately, there's no detailed, I couldn't find any detailed mag from Bayan-Obo, and it's a much more complex deposit. Nolan's also doesn't have a great magnetic signature, but there are a large amount of other carbonatites that are really distinctive magnetically. And again, in this case, without going through the whole source, transport, trap, gradient, driver, and all that sort of thing, I think the approach that's best taken here is a much more pragmatic one, and that is, what we've done in this case is just taken the recently available on the GSQ data portal stitch for the entire state and gone looking for things that could potentially be carbonatites. And I know probably a lot of these have been drilled, but there's about 41 or so signatures that are comparable in scale and similar in characteristic to known carbonatites. And we're about to embark on a process of just screening which one of these are potentially untested. But I think it's too early to say there are no carbonatites or few carbonatites in Queensland. I should have added on this slide a reference to Carl Spandler's paper from this year, because obviously Carl is the one who's coined the term and been involved in work on Brown's Range in relation to unconformity style mineralization, though I guess the model is a variant on a model that I've certainly been involved in working on, and many others around uranium, gold, platinoid, rare earth mineralization. And again, there's quite an established understanding of, in the case of unconformity uranium, of the sources of fluids and metals. Carl's model for unconformity rare earths is a little bit different, but it does involve mixing of a basinal fluid and a basement fluid that have a contrasting salinity, pH and redox conditions that are a fundamental control in a setting that really doesn't have a really strong structural driver, but the structural control at the site of deposition is really strong. So what I put on there on the right-hand side is an existing prospectivity compilation from 2010 done by Geoscience Australia that Terry Myrna and others, that included a lot of those components and is a really good starting point for that style of targeting for this style of mineralization. And then we'll come to the first of two of the styles of mineralization that I think are probably a little bit of an artificial distinction. So what I'm showing there is, I think for about the fifth time today, that the diagram of heavy versus light rare earths in the upper right-hand corner there. Can someone tell me when I've done 10 minutes? I've probably already done it. And the yellow field there is actually the field covered by the Valhalla and the Mount Isa uranium field, data provided by Andy Wild. And what it shows is that the heavy rare earth enrichment in the Mount Isa uranium field is fairly substantial. And that's one of the styles of mineralization that I guess was targeted in that same 2010 compilation of uranium mineralization as a broad grouping of metasomatic copper, gold, uranium mineralization that is, when you look at it, it's early magnetite sodic alteration forming albitites that are overprinted by potassic alteration with copper, gold, and uranium and rare earths. So it's not unlike IOCGs. In fact, I have always felt that the distinction's a little bit artificial. And really what that comes back to is there are a whole series of deposits where what you're seeing is the source, there's a controversy between the source for the metals and fluids as being whether it's a magmatic source or a non-magmatic source. But in the case of Valhalla, for example, there's not an obvious magmatic source for the fluids. In most cases, though, what you do see is that there's an association with an intrusive driver for the mineralizing fluids. And the same thing applies to the IOCGs. So, what's that? Okay, I'll keep powering along. So I think it's good to see that there's work done contrasting the metasomatic and the IOCG styles of mineralization, because in both cases, the question you come up against is, what would you actually map differently? How would you distinguish between pure IOCG targets and IOCG and or metasomatic rare earth targets? And I think that it's partly related to potentially mappable earlier alteration. I misspelled volcanics there, I see. I'm not going to spend too much time talking about this. This has been well presented previously. The Peralkaline Volcanics, like the Peak Range volcanics, they are potentially really a good source for rare earths. I guess what I would say is that in this case, it's probably not a targeting exercise. Potentially the targeting exercise is targeting mineralogies, if they exist, that are more easily, that allow easier extraction of rare earths. So the round top, which is often used as an example of mineralization that is equivalent or an economic target, not unlike this, the mineralizations in yttrofluorite rather than eudialyte. Of course, mineral sands is another potential source, and all I've shown here is the map of Queensland with all the mineral sand occurrences along the eastern coast. And again, there's probably a strong source rock control to the rare earth rich parts of that. And the other thing, and this is something I showed a few months ago as well, when you look at all the Queensland mineral occurrences and then extract the rare earth mineral occurrences from the data set, there are 15 of them. But actually, when you go back and filter that, the Queensland mineral occurrences using mineralogical similarities, you actually get a larger number of potential occurrences that could be screened for their rare earth content. So I'm going to shoot ahead through these because I don't want to steal all Paul's time. But this is a work in progress essentially, and I've already mentioned it has a relationship to a number of other projects that have been presented this morning. So, Paul, I'll pass to you. Sorry for going over time. I'll hand you this and get your presentation up.
Thank you.
Where are you? Cobalt summit.
That's it. Yeah. So that's it, isn't it? Wow.
Yeah, just
Yeah,
clip it on your.
Oh, okay. Thank you. All right. Thanks, Rick. I'm probably going to skip through the first couple of slides because it's essentially what Rick had shown. So I'll just move along there. And I wanted to acknowledge this bunch of people that I saw on Rick's slides as well, but also Dave Purdy and Coralie Siegel and the GSQ also have given us some input, particularly on the geochemistry. So if you look at cobalt, I'm surprised this may be coming up, similar material this afternoon with Dave Houston. The big thing to notice here, first up, is if you have a look at this plot over on the right, 83% of the global resources, reserves and past production is actually cobalt that's estimated to sit on the sea floor. And I'm not going to say anything more about that apart from to highlight that those resources are there and may eventually one day come to be commercialised. What I will say though is this plot over on the left is production from 2011, and what you will see is that it's strongly dominated by stratiform sediment-hosted copper cobalt deposits, and then magmatic nickel copper cobalt PGEs and nickel cobalt laterites as well. So the main point I wanted to make is that cobalt production currently is strongly biased to these three deposit types. And what's probably even more important is down on the right, bottom right here, you'll see that blue area. Can you see that cursor on there? No? Here we go. Go to the right. There we go. Okay, thanks. So this blue area here, I think the number is about 55% of the world's cobalt in 2011 was sourced from the Congo, Kinshasa, the African copper belt, essentially. And what we'll get to in a minute is that a lot of people look at and say, well, these copper belt deposits, are the future for cobalt production. But if you look at the large three fields, you've got the Udakan in Siberia, you have the Kupferschiefer and the copper belt. The copper belt is really the only one from which cobalt is mined. And that's attributed by various people to different reasons. But I think probably most sensibly by Hitzman to the presence of a very, very strong mafic basement in parts of the African copper belt. And it's interesting that reading some of his stuff is that Kamoa-Kakula, the Ivanhoe big deposit, essentially is cobalt. I don't know whether you'd say poor or barren. So even within the African copper belt, there is a big difference in the cobalt content. And then the other thing I wanted to point out is the grade of deposit types. So those three big deposit types, the copper belt, the nickel cobalt laterite, and the magmatic nickel copper PGEs, you will see that the copper belt deposits have much higher cobalt grades in green there, and then you go down through the laterites, and then by the time you get to the magmatic nickel copper PGE deposits, really your cobalt grades are getting pretty skinny there. You'll see over here sort of 0.06 at Sudbury and Raglan, etc. So whilst they have cobalt and they do produce a reasonable proportion of the world's cobalt, they're relatively low grade, and it's definitely a byproduct. So Rick introduced this sort of table. So what I've done here is take these are the key deposit types from which cobalt is pretty much either currently produced or known to be enriched. And you'll see that a lot of them, certainly from the top there, you go, strata-bound sediment-hosted copper cobalt, copper belt style, magmatic nickel copper, nickel cobalt laterites, and then you go down to the bottom, IOCG and VMS. So there's some pretty well-known deposit types there that have been pretty heavily, I guess, studied and explored. So I'm not going to touch too much further on those. Because there's been some great studies. I was looking at the magmatic nickel copper PGM study by GA that came out, I think, about 3 years ago, and fantastic work. And there was another GA IOCG targeting study a couple of years ago as well. So there are those deposits that are really well known, but then there is a bunch of other cobalt-bearing deposits that I'll touch on in a minute. So what I did was put the word map together from that table, which is you can see along the top. There's the source, the transport architecture, the trap, the gradient, the driver, etc. So if you put all of those words together, this is essentially what comes out, and you'll see that the big words: fault, ultramafic rock, igneous activities, serpentinites, fluid mixing. So it gives you a bit of a guide as to what we should be starting to think about if we're looking for prospective areas for cobalt mineralisation. So before we get on to that, there are four other styles of mineralisation that are cobalt rich, which are very well not known. So I'll quickly run through them. There are the black shale hosted nickel, zinc, copper and cobalt deposits. There's really one premier deposit in the world, which is in Finland, the Talvivaara deposit, which is interestingly enough a heap leach operation. So essentially, it's deposition of your metals in what are regarded as anoxic, very still redox stratified basins. There's the metasedimentary cobalt copper gold, which is probably the best known of these secondary cobalt types. And it's basically known, I guess, from the Blackbird mining district in central Idaho. And I think it's what's referred to as the Idaho Cobalt Belt style deposits. And what it essentially is aluminous clastic sediments that are hosting essentially early pre or synmetamorphic mineralisation. Upper green schist to amphibolite facies. And there's a very strong presence often of biotite scapolite schists through those deposits. They're sometimes ascribed to the IOCG clan, but really they form their own cobalt-rich group. So an interesting metal association, cobalt, copper and gold. And the Mount Cobalt deposit up here in northwest Queensland has been included in that category by Slack et al. In 2013, which was a big USGS study into cobalt deposits. Now the other cobalt style of mineralisation, I guess that's probably more important up here in the northwest is the carbonate-hosted copper cobalt deposits, with the prime example being Walford Creek. And when we look at the Northwest Queensland Atlas after lunch, we're going to have a really good look at Walford Creek and a lot of the data from there. And then there's another deposit called Ruby Creek in Alaska, which is somewhat similar. And I guess the key points: calcareous or dolomitic host rocks, commonly abundant pyritic sedimentary rocks, dolomite breccias, and lead and zinc commonly present as well. So we've taken essentially the GA type approach here and said, well, what are the mappable criteria, and then applied them statewide, rasterised them to integrate them together to give you those maps of I guess, prospectivity. So this is just an example here of the black shale hosted mappable criteria. So you'll see that there are the terrain bounds, ultramafic rocks, and the deep marine rocks, as well as we've taken and normalised the state stream sediment database and chosen out the nickel, zinc, copper, cobalt chemistry. So we put those things together. So we did that for those three, I guess, secondary copper styles of mineralisation. So up in the top left there, you will see the black shale hosted prospectivity. You'll see the carbonate hosted copper cobalt, and then the Idaho copper belt style of mineralisation. So that's basically looking at those mappable criteria for those three different types, deposit types. But also we've basically thrown the kitchen sink at it and said, well, from all of those 9 categories of cobalt deposits, what are the key elements? And so we've taken 9 mappable criteria and put them all together. And essentially the rationale is, well, we have these deposit types that we know about. Yep, we can search for them. We know what their characteristics are. But really, what we want to be finding is there a new style of cobalt deposit that doesn't look like anything we've seen to date, and hopefully is richer, and we're not going to find it if we're looking for those mappable criteria only from the previous deposits. So let's start putting them all together and see if it starts to pull anything out. And I guess what you'll see from this diagram is that there's obviously northwest Queensland, which is, I guess, dominated by these sedimentary type host rocks. And then and also the cobalt geochemistry is pretty strong up there. And then you'll see these other red patches are very strongly biased by where the ultramafic rocks are in eastern Queensland. And then you can see where the terrain boundaries that we've basically that Karen Connor modified from the FrogTech terrain boundaries to ensure that they were more representing actual deep-seated structures. So, in summary, the current exercise, it's most relevant to exposed terrains. We're still to add the geophysical constraints really to move undercover. We've not dealt with subsea deposits here. So in summary, there's 5 well-described and heavily explored deposit types, and you can see the alphabet soup there of nickel, copper, magmatic, IOCG, VMS, etc., etc. But there are 3 other poorly defined and understood deposit classes that have the following broad elements in common. And really the really strong piece that links these cobalt deposits is the ultramafic or mafic relationship. Not always as host, as nickel laterites often are, but not always as host. The variety of metals in the mineralisation, but cobalt, nickel and copper are a very strong thread through those deposit types. And then thirdly, those 3 poorly defined deposit classes are all hosted in sedimentary rocks, albeit in a variety. So there's the black shale, there's the carbonate, and then there's the siliciclastic metasedimentary style of deposit. So it's interesting. So cobalt present in a lot of these deposits that we're already looking for. but also there are these other types that are very poorly understood and I think are probably more likely to be found simply because people have not really been looking for them before. So I'll leave it at that. I see we're getting to lunch. Thanks.
Thanks, Paul, and thanks, Rick. Does anybody have any questions for either Paul or Rick? Nick does, and Derek's coming with a microphone. Stand in front of the camera.
Cheers, thanks. There's a significant issue here for many of us explorers in that it's all very good with the elements in the ground, but there isn't actually a market for them. So there's a whole question about the geometallurgy. There's a whole question about resource efficiency, as the Europeans would say, about getting all the other components out of complex metallurgical systems. But in Australia, there isn't a way to produce any of this stuff if you actually dig it out of the ground. So actually raising money for people to go and explore it is virtually impossible, unlike gold or copper or something like that, where there's an obvious market. So I don't know where we're going to go or how we're going to create the market that will actually drive the exploration. And we'll follow up privately on all the finished cobalt stuff, which I can give you some background on. Cheers.
Yeah. Did you want to say anything, or? You go first. Okay, I can go. It's the market. Well, the market. It's a good point you raise. Oh, sorry. It's a good point you raise, Nick. And I guess standing here thinking about how we can discover these things. Well, there's 2 points. A, how we can discover them. I guess we can't influence as geoscientists here the market so much, but I think there are going to be a lot of external influences changing that over the next 10 years. Apart from all the talk we hear about electrical vehicles and wind turbines, et cetera, et cetera, et cetera. So it will be interesting to see how that plays out. And I guess another thing that feeds into that is also the globally we're seeing the interaction and the input from governments on this. Mainly, I think Matt might have mentioned earlier about rare earths being geographically constrained, and we also see from cobalt, the cobalt where the production is coming from is very tightly packaged. But I'll give myself a plug for this afternoon. We're going to talk about rare earth element processing. And it's one of the things that it's been great that the project started just this year looking at rare earth processing and what the impacts of rare earth processing is and how difficult it is to do, and are there other ways that we can do that in a much less capital intensive way and a much less detrimental outputs manner. So I'm going to talk about that this afternoon, but that's one way we're trying to improve and understand different ways that we can process some of these critical metals so that we actually can do it easily on shore. Yeah, thanks. Did anybody else want to say anything about? That's a very general question Nick asked. So.
I can talk about government precinct strategies at a federal and a state level, but Mav has a question and Derek will hand him the microphone. Maybe we'll come back to that later.
Thank you. I noticed that you didn't mention Cobalt, Ontario, or the 5-element vein sort that people seem to like geologically. Are they too insignificant to talk about?
I did have the 5-element veins on that table if you'd squinted to read through the text. But yes, they're too difficult to talk about. These are the categories, for example, the black shale and the carbonate, copper, cobalt, etc., are much more easily characterised. I guess from my reading of the 5-element type cobalt deposits, and it sounds like they were pretty much one of the earliest recognised in terms of geological thinking. But when I looked at them, they were so difficult to understand with their different host rocks, different metamorphic grade, different fluids. You have a good look at them, and people talk about what's the driver or the fluid source here, and you will read all the way from metamorphic fluids to magmatic fluids to to basinal fluids. So yes, your comment is correct that they were just a bit too difficult to tackle in a coherent way. Yeah.
Paul? Derek will bring you the microphone.
Thanks, Paul. On the prospectivity model, just a question. For the Maldizer block, where there is exposure, you got high prospectivity. Where there's
Yes.
no exposure, you got low prospectivity.
Yes.
What elements in the prospectivity model make the difference there between high and low prospectivity, which you found difficult to assess?
Well, if you look at those elements that we put together for Cobalt, really the only element that is essentially going undercover is looking at those terrain boundaries, okay? Because FrogTech have mapped those undercover. But the next step that we're aiming to do with this program is to say, well, there is the other very important rock type, which is an impact, is your ultramafic rocks. And as Rick was showing, looking at the carbonatites undercover and the magnetic data, so that's the sort of thing that we're aiming to start incorporating undercover. So that, you know, if you could identify new ultramafic complexes undercover, under relatively thinnish cover, then that would open up whole new fields. So that's what we're looking for. Yeah.
I just wanted to comment on that briefly as well, because it's a really important question, because and a lot of the times what people do when they're doing this sort of analysis is they develop two sets of targets. One is based on exposure, where we have a lot of information and can do a completely different sort of analysis, and usually it's a big data integration and thinking about much more complex concepts exercise. And then when you go undercover, the big problem is there's no information or very little information. And when you look at a lot of the regional targeting for the various different styles we talked about, you're going back to the terrain boundaries that are established from, like the FrogTech style things that Paul talked about, and looking at the OSREM, the seismic tomography, or OSLAM magnetotellurics where it's available, and a whole lot of really quite regional data sets. And it really just throws into light how hard it is to target these things undercover. But yeah, you really have to divide those two settings into different approaches, which is what most people do.
We also have a question from online. Murray Hutton has asked, so what is the cobalt endowment of the Mount Isa tailings? Which we've had some discussions about recently, and I guess the answer is not entirely sure, and the Glencore people here are not going to say. So 42, yes, Hitchhiker's Guide to the Galaxy. Okay.